Talking of loaded springs, in loaded spring we have a spring to which a mass is attached. We can attach the mass in horizontal direction and also we can attach the mass in vertical direction. That means it can have vibration in horizontal direction as well as in vertical direction. Let us discuss the case of vibrations of a horizontal spring. Let we take a spring, attach it to a rigid support with spring constant K and mass factor is equal to M. Now mass factor is inertia factor. Now we know that when we are displacing this mass in this direction, a restoring force F will be applied in this direction, and that restoring force will be opposite to the displacement. L will be proportional to the displacement. That means less is the displacement, less is the restoring force, more is the displacement, more is the restoring force. That restoring force will be equal to minus K times Y, where K is the spring factor and minus denotes that the restoring force is opposite to the displacement Y. Now, from the study of time period of simple harmonic oscillations, we know that time period is equal to 2 pi root of inertia factor by spring factor. In this case, the inertia factor is equal to the mass attached to the spring and spring factor will be equal to the K. So our time period comes out to be 2 pi root of M divided by K. Easy. Where M is the mass, K is the spring constant, and that spring constant is given and mass is given. 2 is already given. Pi is 3.14. We can calculate the time period. In talking of the vibrations of a vertical spring, let us take a spring and attach a mass M to its end. Now, when we attach a mass to it extends by a distance of L under the effect of the weight mg, but it doesn't oscillate up and down. Now, we know that when the mg is vertically downwards, there should be an upward force, upward restoring force, which will restore the shape of this spring. And that restoring force should be opposite to the mg. So, that restoring force will be equal to F is equal to minus KL. Because as L will be large, the restoring force will be large, but the restoring force is opposite direction to that of weight. That means we have got the negative sign. Now this KL, taking the magnitude only, KL should be equal to mg, as those are opposite, but their magnitude is the same. So KL will be equal to mg. From that, the spring constant will be equal to mg divided by L. But it should be borne in mind that it doesn't oscillate. It extends by a length of L. From that, we calculate what is the spring factor. K is equal to mg divided by L. Now, what are we going to do? We are going to displace this mass by an extra length of y, and by that extra length y, a restoring force will be developed in this spring, which will make it to oscillate to and fro in vertical direction, and we will get the vertical vibrations. In that case, the effective restoring force developed in this spring F will be equal to minus Ky. So by this extension, it is not going to vibrate, but by an extra extension of Y, it is going to vibrate in the vertical direction. So the effective restoring force, here also there is restoring force, but due to the extension by the weight applied, here is the effective restoring force. That effective restoring force enables this spring to vibrate in the vertical direction. This is a linear oscillator. Time period is equal to, T will be equal to 2 pi root of inertia factor by spring factor. Here the inertia factor is the mass attached to the spring. So T will be equal to 2 pi root of M, and the spring factor as already calculated here, K is equal to mg divided by L. Now M and M goes, so T is equal to 2 pi root of L divided by G. This is same as in case of simple pendulum, but this thing should be borne in mind. These are vertical vibrations, but those are angular simple harmonic vibrations. In simple pendulum, the mass vibrates in this direction, but in vertical vibrations or vibrations of a vertical spring, the mass vibrates in vertical direction, or in case of horizontal spring, the mass vibrates in this direction. So vibrations of a spring are linear simple harmonic oscillations, and vibrations of a simple pendulum are angular simple harmonic oscillation.